Good morning also from my side. So it was very nice to already get the motivation of why we want or why we need parameterizations for these submesoscale, these small scale features. And I will try to continue with this and introduce some basic or some early thoughts on how we plan to come up with maybe such a parameterization and what are difficulties there. And I hope that I can convince you that dissipation of these ageostrophic effect, that this might be an important aspect of this. So let me start with a very basic schematic. So of why or how the ocean actually dissipates energy. So this is I think still a very or quite unsolved conundrum. So we have certain processes in mind, but the quantification of these processes is largely lacking, I would say. So in our view that the ocean is forced on the rather intermediate or larger scales, so scales up to or around 100 kilometers. And then on these scales, the dynamics are largely geostrophic. And then there is this famous result by Charney that when you have this quasi-geostrophic turbulence and the energy cascade is projecting or is transferring the energy towards larger scales. So and larger scales are, the molecular fluxes and molecular dissipation has a hard job of getting rid of the energy. So there need to be other processes involved. So candidates for this are, for instance, when you have frontogenesis, you might stimulate ageostrophic dynamics, or as we have heard in the last talks, there could be Lee waves, and maybe there could also be something like spontaneous or stimulated loss of balance. So, and these processes, they might kind of transfer energy from the geostrophic flow into another regime, the ageostrophic regime. So, and so what is the consequence of this? So it was shown already, I think, in 2010 by Moolmaker and others that as soon as you have a dynamics or a flow that is not purely geostrophic anymore, but also ageostrophic, that suddenly your strictly your strictly inverse cascade that is governed by the geostrophic flow is not so strictly it's not so strictly towards larger scales. You can have also a flux, an energy flux towards smaller scales. It was already mentioned in the previous talks. And what I try to do together with Carsten is to simulate in a very idealized Eddy type of simulation where we could basically set the background state of the flow. We could determine this by the shear of the flow and by the stratification of the flow, and there we could suggest, or we could put different initial conditions and different dynamical regimes. So we characterize this by the Richardson number, so by the stratification divided by the geostrophic shear. And when we increase the Richardson number, when we decrease the Richardson number, so high Richardson numbers typically go together with very geostrophic conditions. So, and you can see that for this geostrophic conditions, you have a largely inverse cascade. But when we then decrease the Richardson number by the background state, then this inverse cascade suddenly turns to a forward cascade. And that shows that depending on the background state, you can have a very different response of your regime, very different response of your turbulence. And that is something that we now would like to explore a bit closer in a more realistic simulation than that. So, but this is of course complicated, as we also have seen in the previous talks. These ageostrophic dynamics are associated with high Rossby numbers, and a high Rossby number typically means very small scales, or at least a high horizontal shear of the flow or vorticity of the flow. And these small spatial scales, they are of course, then you need a very high resolved ocean model, and they're also quite rapid. The instabilities which originate from these scales are also quite rapid. So we also have short time scales. So this is kind of in a way nice, because then we don't have, if we have our high resolution models, we don't need to run them that long. So a couple of months or a year or something like this is already sufficient to see some aspects of this. So Yeah, but in order now to simulate these small and fast motions, we would like to zoom into the ocean, because globally, on a global scale, it's really roughly it's really complicated to resolve all these dynamics. So what we came up at the Max Planck Institute is with a simulation that we call the submesoscale telescope simulation. So the telescope means that we kind of, with our resolution, we zoom into a certain region of the ocean. So here I've shown you a figure of the spatial resolution of this model. And here in the North Atlantic, so we are interested in this focus region in the North Atlantic. We have a resolution that is up to 530 meters, and then it's getting coarser and coarser away from this, and up to 11 kilometers here around Australia. And this simulation we run for a couple of months typically. So and that hopefully that I mean the dynamics here around Australia and the Southern Ocean, they are probably quite screwed up. So, but we hope that with this shorter simulations that we don't get these imprints of these bad circulation that we have here. So that yeah, we still have a relatively qualitatively nice representation of the features in the North Atlantic. So in the vertical, we have 112 vertical levels, and it's basically that we have a resolution that is smaller than 5 meters in the upper 200 meters. So we also want to focus on the upper ocean with this type of simulation. So this is basically the initial condition of this simulation. So we initialize this condition with a coarser simulation, with a 10-kilometer simulation. And what you can see here are the submesoscale. There it comes. Now it also looks a bit different for you. So what you can see is that these fronts actually they break up and they create instabilities, and these instabilities are on spatial scales which are much smaller than the baroclinic scale, the first baroclinic Rossby radius, and therefore we would like to call them submesoscales. So and now the question is, with these submesoscales, are they, what type of dynamical regime are they? So they could, in principle, they could also be geostrophically balanced. So it's not, so they not necessarily have to be ageostrophic. So they not necessarily have to be in a different dynamical regime than what is known from the larger scales. So to look a bit closer onto that, we look at the Rossby numbers, the local Rossby numbers. So that's basically the vorticity that we diagnose divided by the Coriolis frequency, by the Coriolis parameter. And what you can see here that we have indeed actually quite high Rossby numbers, positive Rossby numbers in particularly in the Gulf Stream front, but also here to the south in different regions, and you can see some spiral like eddies in these regions here. Actually, there's a soup of these type of fronts and eddies where you have these high local Rossby numbers. And these high Rossby numbers, they when you think of quasi-geostrophic theory, where you derive your quasi-geostrophic equation with a small parameter, which is typically the Rossby number, and then high Rossby number typically indicates that your quasi-geostrophic approximations are not valid anymore, and this is why we think that we are here in an ageostrophic regime. So this is now the same figure as before, and I've indicated two regions. One here south of the Gulf Stream front, where we have this enhanced submesoscale activity, but then also north to the Gulf Stream front, we don't see so much submesoscale activity. And when we now plot the histogram of these vorticity values, then that is what is shown on the right-hand side here. So the gray curve is actually the overall Rossby number, and then we have the upper, the orange curve is this upper region, and that basically indicates that we have hardly Rossby numbers that are larger than 1, and in particular they are not smaller than -1. But then in contrast, in region 2, in the south of the Gulf Stream front, we have the tail of the distribution actually goes quite far into Rossby numbers which are larger than 1, and we also have some Rossby numbers which are smaller than -1. That would indicate actually for negative PV and therefore potentially symmetric instability. How well we can resolve or represent the symmetric instability is on a different, it's a different question, but potentially there could be some kind of these instabilities. So, and now when we zoom into this, into a particularly on a particular eddy, so here we have the larger scale area, and now this upper right panel is the right corresponds to the black triangle. You can see the Gulf Stream front here, and now we are zooming onto one spiral eddy that is seen here. These submesoscale eddies, they typically or often come in the spiral form. There's also nice papers out there why this why people think it makes sense that these are spirals. So, but this is another story. So, and now we want to look how these eddy actually, or how these dynamics actually, how does the dissipation look for these eddies? So therefore, we are looking closer to one of these eddies. So here we have this eddy. It's a cold core eddy, and we are making a transect through this eddy. And then on the bottom, you see the temperature of this transect. So you can see that here we have the mixed layer, or the pycnocline where it's strongly stratified, and then above that we have the mixed layer where stratification is weak. So here's a Rossby number again. So in the upper ocean, you see this is actually at 50 meters here. So in the upper ocean, you see the spiral eddy, and you can see that the high Rossby numbers, they basically reach until the base of the mixed layer. So, and now we also look at the dissipation, and when I say dissipation, I mean in this case we diagnose the dissipation that we are using in the model. So we have a biharmonic operator that dissipates momentum, and then from this you can calculate the energy dissipation. So, and the energy dissipation, or this term, actually comes with two parts. So one is a flux term, and the other one is a negative definite term. And so we are only diagnosing this negative definite term. So this is basically where actually energy is not redistributed, but really taken out of the system, really dissipated. So, and as you can see that the dissipation here, it's quite enhanced in the mixed layer, and then suddenly below the pycnocline, there's nothing. So, and that is, I think that corresponds quite nice to the figure to the left or in the center here, that also where the Rossby number is dropping down, and where we don't have this ageostrophic dynamics anymore, suddenly we also don't have the dissipation anymore. So there appears to be a strong connection between the dissipation and the Rossby number. And as we have heard in the previous talk, so most likely this is associated with this downscale energy flux, with this forward cascade, if you want to call it like this. So so this is now for one particularly eddy, one particular situation. So when we look on the more larger picture, then what I've plotted here to the left-hand side is the geostrophic Richardson number. This is again the Richardson number that I've shown you on the second slide, I believe. So where we could show that the strength of the forward cascade is depending on the Richardson number. So therefore, we now also want to see if we can see a similar effect here. So if dissipation, for instance, correlates with the Richardson number, and whenever you have small Richardson numbers, you expect these ageostrophic dynamics to dominate. So, and as you can see on the lower panel here, actually, this seems to be the case. So where you have this strong, where you have the low Richardson numbers, you have a really enhanced dissipation. And then when you think of in terms of a parameterization, so like maybe we can find a connection between the dissipation and the Richardson number, or the state of the background flow. And this is what we are up to. But still, if you only have dissipation, so this is then probably not enough. You also need a forcing of your subgrid scale energy. And the forcing that, at least in this model, is basically baroclinic instability. At least that's what I thought in the beginning. And maybe that's not enough, as I will show you in a second. But this baroclinic instability, this forces eddy kinetic energy by this buoyancy production term, this W prime B prime term. So, and this is shown here on the right-hand side, and it's a bit sketchy. So this is a bit, yeah, so these are kind of preliminary results, because we also see actually negative values of this W prime B prime, but this is also because we are only this is only diagnosed at one depth level. So probably we need to expand this to the overall mix layer. But anyway, if you now divide the dissipation by the production, then you would expect, if everything is local, that you have numbers which are strictly smaller than 1. But what you can see here, that where this is also a logarithmic plot here, so everywhere where it's blue, actually we have this. So we find that the dissipation is always smaller than the production, but you can also see that there are red spots, and this is where actually the situation is different. And that points that either we have transport of energy, so of course this is also not really unlikely in this, that we have advection of energy, but it could also point that there are also other instability processes active, for instance, barotropic instability or so on, so which then also might generate this energy on the small scales. So now to briefly maybe show a kind of a scaling attempt. This is really preliminary results, but when you just plot your W prime B prime against the Richardson number, so I did some binning here. So, and then you can see that actually seems to be a power law between the energy production and the Richardson number, and the same seems also, not the same, but a different power law seems also to hold for the dissipation. And then when you now check the power law that is for the fraction of that, then you can see that here for low Richardson numbers we actually have a fraction that is larger than 1, so there has to be something else. And here there might be something else as well, but here we might also get another power law that then maybe can use for parameterization. So, and the idea, the rough concept of these parameterizations would be that we parameterize this W prime B prime from submesoscale parameterizations which are already out there. For instance, Fox-Kemper or Stone, they come up with some ideas, and then that we then parameterize these with the Richardson number. We parameterize this ratio here, and then we get an estimate of the energy dissipation. So so I think I skip over this. This is dissipation at depths. You can also see it that we have dissipation at larger depths, or albeit much smaller and very close to the western boundary current. We also have a different simulation where we have this this zoom or this focus region in the South Atlantic, and there you can see also these Agulhas rings and this strong submesoscale activity. It's different when you simulate this in another season, but this is kind of maybe for the sake of time I just go over this and I quickly summarize. So we have seen that we have in the simulation we found the submesoscale dynamics. We found that the submesoscale dynamics are often associated with enhanced dissipation, and then we try to come up with this kind of scalings for the dissipation, and try to find whether this can be useful for parameterization. So now I'm at the end and like to thank you very much.